The graph of kinetic energy and potential energy and total energy you can see in a diagram. So here, so this is extreme position. So this is positive extreme position. This is negative extreme position. So where the amplitude is minus a and here it is plus a. Now we can write here some values. So you know that at mean position x is equal to 0. At mean position x is equal to 0 and velocity is maximum. So let me write the formula of kinetic energy at mean position. So you know that kinetic energy formula is 1 by 2 m omega square a square after substituting x is equal to 0. Because kinetic energy formula is, this is kinetic energy formula. In that formula, if we substitute x is equal to 0, we get this is a kinetic energy. And in a potential energy formula, if we substitute x is equal to 0, we get potential energy 0. Means in simple word, at mean kinetic energy is this and potential energy is 0. Now we know the formula of the total energy also. So total energy formula is 1 by 2 m omega square a square. You can see here at mean kinetic energy is 1 by 2 m omega square a square, which is equal to the total energy. So here we can write at mean kinetic energy and total energy both are same. Now the second case is at extreme position. At extreme, you know that x is equal to a plus minus a. If we substitute x is equal to a, at extreme x is equal to a. After substituting the value of x is equal to a, we get kinetic energy is equal to 0. And in potential energy formula, if we substitute this x is equal to a, then we get potential energy is equal to 1 by 2 m omega square a square. Or you can write instead of m omega square, we can write k also. We get formulas for kinetic energy and potential energy at extreme. Now here we can write here at extreme potential energy and total energy both are same here. That you remember. Now after that, as the particle oscillate, energy changes between means energy changes. At the mean position, the energy is entirely kinetic energy. You can see here is the mean position. So here, so this is the potential energy graph. Let I show the potential energy graph by blue line. So this is potential energy graph. You can see this blue line is the potential energy graph. Okay. Means at mean, you can see here at mean potential energy is 0. So here potential energy is touching to the 0. Okay. And at extreme, you can or we can say that at extreme potential energy is what? This maximum. You can see here this is extreme. The potential energy is maximum here. So at these two dots, and which is equal to the E. E means the total energy. Okay. Similarly, I can show here this kinetic energy graph. Kinetic energy I will show it by yellow. So this is the kinetic energy graph. Now kinetic energy in a kinetic energy graph, you can see here kinetic energy is 0 at extreme. You can see here this is extreme position. So kinetic energy is 0. And at mean position, kinetic energy is maximum, which is equal to the total energy E. So this is the kinetic. So means kinetic energy varies. Now at this position, you can see here this position. At this position, both the energies are same. Now at what displacement both the energies are same, that displacement we obtain. Now we can use the condition if kinetic energy and potential energy both are same. So let I write the kinetic energy formula. So this is kinetic energy formula. Half k a square in a bracket a square minus x square, and this is potential energy formula. Okay? half m omega square x square. Okay? Or we can write, instead of this, we can write k. Then this k and this k get cancelled. So we get formula 1 by 2 a square minus x square is equal to 1 by 2 x square. This 1 by 2 get cancelled. So you get a square is equal to this x square plus x square. So a square you will get 2x square, or x is equal to, or x square is equal to a square by 2. So we get, hence x is equal to a by root 2. You can see the formula here. X is equal to a by root 2. Now you note one thing here. When x is equal to a by root 2, both kinetic energy and potential energies are same. So you can see here the 2 points. So here kinetic energy and potential energy, both the energies are same. That time displacement you can see here, we shown in a graph. It is a by 2 minus a by 2 or plus a by 2. So plus minus a by 2. Both the energies are similar. Kinetic energy is equal to potential energy. Once in a board exam question is asked, at what displacement both kinetic energies and potential energy are same, then displacement is equal to a by root 2, amplitude divided by root 2. Now next article is simple pendulum. First thing, what is simple pendulum? So we talk about the ideal simple pendulum. An ideal simple pendulum is a heavy particle suspended by massless, inextensible, flexible string from a rigid support. We are considering massless, inextensible and twistless, we can say that instead of this, twistless string from a rigid support. It is called as ideal simple pendulum. Now we can draw here simple pendulum diagram. This is support, rigid support, and this is string. To this string, if we hang a heavy particle, or we can, instead of heavy particle, one more word we can use, point mass. We can use the word point mass also. Ideal simple pendulum is a heavy point mass suspended by massless, inextensible and twistless string from rigid support is called as ideal simple pendulum. Now, practical simple pendulum. Practical simple pendulum is what? Practical simple pendulum is small heavy sphere. Heavy sphere means, you can see here we hang here as a bob. Heavy sphere, or we can say that bob. A small heavy sphere suspended by light inextensible string from rigid support. Generally here, practically the massless string is not possible. We cannot consider massless string. So here massless word we are not used. So practically, instead of heavy point mass, we are considering a heavy sphere or heavy bob. Bob means a metal sphere which is hanged to a rigid support by a string. This is a practical simple pendulum. You can see the diagram here. So this is a diagram. This is rigid support and this is a heavy sphere, or we can say that bob, which is hanged to a support. In the displaced position, when the bob is displaced, in that position B here, the forces acting on the bob, forces acting on bob are, the first force is tension in string. The first force is tension in string. Second force is weight, mg. Two forces are acting on this bob. The first force is tension, you can see in a diagram, tension T, and second one is weight. We already learned conical pendulum article. In that also two forces are acting on bob. First is tension and second one is weight. Same forces are acting here. Now here we have to resolve this weight mg into two components. You can see in a diagram this weight mg is resolved into two components, mg sin theta and mg cos theta. Okay. mg is resolved into two components. First one is mg cos theta and second one is mg sin theta. These are the two components of weight mg. Now here you can see a diagram very carefully. So this mg sin theta, so this it pull the bob towards the mean position. This mg sin theta pull the bob towards its mean position. You can see here that this is the direction of the force or direction of the component mg sin theta. So this mg sin theta we can write as a restoring force. So restoring force is equal to mg sin theta. Now we put the minus sign here. The minus sign indicate that as this F increases, means restoring force increases, this theta decreases. Means theta and F, they are oppositely directed. So minus sign is here. Now here theta is very small. Theta is very small. So we can write F is equal to mg into theta. Sin theta we are written as a theta. So this is the restoring force. In magnitude we are written. We are not written negative sign because we consider the magnitude. For small angle theta, you already learn in geometry. If this angle is small, then this angle theta is equal to this arc x divided by the length of the string is L, x by L. So here you can see here for small angle theta, we can write it is equal to x by L. Now instead of theta, we substitute x by L. So we get restoring force is equal to minus mg into x by L. Or when we want to write only the magnitude, no need to put the minus sign. So this is equation number 1. Now here by this equation we can write. So as here m is constant, g is constant, L is constant. So F proportional to minus x. So we get formula F proportional to minus x. So F is the restoring force, x is the displacement from mean position. So restoring force proportional to displacement and negative sign indicate that they are oppositely directed. It means that this motion of the bob of simple pendulum is SHM. When we get restoring force proportional to minus x, it means that it is SHM. It is SHM. So restoring force directly proportional to displacement here, and both are oppositely directed. So we can write this is SHM. Now here period of the oscillation of pendulum is given by. Now we have to write formula of period. Now we already derived this formula, period is equal to 2 pi by omega. Or we can write 2 pi upon acceleration per unit displacement. So this is the formula of period. By using this equation 1 is equal to F is equal to minus mg into x by L. By using that we can write ma is equal to, you know that F is equal to ma. So ma is equal to minus mg into x by L. Now we can cancel this m and this m is get cancelled. We get acceleration. Acceleration is equal to minus g into x by L. This is the formula of acceleration we get. Now we have to obtain this formula. Listen, acceleration per unit displacement means x we have to shift to the acceleration side. So a by x is equal to minus g by L. In magnitude only g by L. In magnitude only g by L. So here, so this a by x is what? Acceleration per unit displacement. And this acceleration per unit displacement we have to substitute here. In this G by L we have to substitute here. We get expression for period of simple pendulum. Substituting this acceleration per unit displacement in an expression of capital T, we get T is equal to 2 pi in a root G by L. Listen here, we substitute only 2 pi as it is. Acceleration per unit displacement is what? G by L. So after writing this in a proper word, we can get the formula 2 pi under root L by G. And this formula is the expression for period of simple pendulum. Now, from equation 1, from this period of simple pendulum, we can conclude following things. The first one is period of simple pendulum directly proportional to square root of length. So it means that the first conclusion is T proportional to square root of length, or we use here capital L, sorry, I can write capital L. So this is the conclusion. Means period depends on length. How it depends? Period directly depends on square root of length. Second conclusion, period of simple pendulum is inversely proportional to square root of acceleration due to gravity. Means T inversely proportional to square root of acceleration due to gravity. So this is the second conclusion by this formula. Now the third one, by formula we can write period of simple pendulum does not depends on mass. You can see here period depends on L on G only. The mass term get cancelled here. So period depends on the L and G, not on the mass. So the third point we are written period independent on mass. It means that in problems question may be asked like this. If this is simple pendulum, so where we use a mass M for the bob, mass of the bob is M. Now the same length string, and if we double the mass, means mass is 2m, then how much is the period? The options are T, 2T, then T by 2, and the second last option is 3T. Listen, if period at the point 1 means position 1 is T, the period in the second position is also T, because period does not depend on the mass of bob. So here also the same period. So this is the conclusion. Period depends on the length. So I consider the length of the string in both the cases is same. So period does not depend on the mass of bob, that you remember. This is third conclusion. And the fourth one, period of simple pendulum does not depend on amplitude. So this is also very important. So let I explain this also. If we consider, so this is simple pendulum. So this is a bob. Now here, so this bob is moving up to this 5 centimeter, and this side also 5 centimeter. Means the amplitude is 5 centimeter. The same simple pendulum, you know that after some time what happened? The amplitude goes on decreasing. The same bob not going to the 5 centimeter, it may goes up to the 2 centimeter. Let I consider it goes up to 2 centimeter. Then also the period is same. If in this case the period is T, the second case also the period is T if the length is same. If the length is same, G is same, means acceleration due to gravity at that place, then the period is same. Means period does not depend on the amplitude. So this is the conclusion of this formula. Next article is seconds pendulum. What is seconds pendulum? Seconds pendulum is a simple pendulum. Seconds pendulum is simple pendulum whose period is 2 seconds. This is very important. If we consider simple pendulum and the period is coming 2 seconds, then it is called as seconds pendulum. simple pendulum with period 2 seconds is called as seconds pendulum. Now here, you know the formula. T is equal to 2 pi under root L by G. This is the formula for simple pendulum. Now if I substitute period is 2 seconds, T is equal to 2 seconds. Then what we get? For seconds pendulum, period is 2 seconds. Now we get this equation. This 2 get cancelled. And if we obtain formula of L, L is the length. Then how much length we get? So we get a length is equal to G by pi square. So here we get, after cancelling 2, we get 1 is equal to pi under root L by G. Squaring both side we get, or we squaring both side, 1 is equal to pi square L by G. So by using that, we are written here L is equal to G upon pi square. Now you know the value of G. Value of G everybody know. The value of G is 9.8 approximately, and then pi is 3.14 square. So 9.8 divided by 3.14 square is, I think, 9.84. So it is coming 0.99 meter. So it is coming 0.99 meter, means approximately 1 meter. So simply you can remember here, if the length of the simple pendulum is 1 meter, then we are getting period about 2 seconds. We get period about 2 seconds. Now distinguish or difference between this conical pendulum and simple pendulum. Now here the trajectory. Trajectory means the path followed by this bob is circle. And here the trajectory is what? It is a vertical circle like this in simple pendulum. Second one, kinetic and gravitational potential energy constant. But here kinetic and gravitational potential energy are interconvertible. The energy is conserved, but they are interconvertible because it's a vertical circular motion. We learn vertical circular motion article also. In that, kinetic energy and potential energy are interconvertible. Next one, you can see here, horizontal component of force due to tension is necessary, and here tangential component of weight is governing the force. Means here we know the restoring force we learn. Now here period is given by this formula, and it is given by this. For same length, this period is greater. Period of the simple pendulum is greater. Other 2 points also you can see here.